Welcome to your independent study in structural equation modeling. So course calendar is really flexible, but in general we're going to learn CFA, path analysis, the whole SEM, which puts those two together. We'll learn how to do group differences, and then the last 5-ish weeks will be dedicated to your final project. There will be 3 discussion boards. This is really just a chance for you to find an article, dissect it, start figuring out the parts and pieces in articles, what's being reported on, what do you think is good, what do you think isn't good, and starting to interpret these models. So you're going to annotate something and then we'll post it to the group, and that way you can see other people's annotations and you can get several articles and look through them. Final projects will be CFA, path analysis, or SEM with real data. This should be an AERA proposal, so about 2,000 words. You could do a mostly full article if you want to go that route as well. Your choice. I have data. We should chat soon about what kind of data you want to use. This class will be using AMOS. And AMOS is part of SPSS, so they kind of will be going hand in hand, so you will need both. There are grad packs for both. For the SPSS, make sure you have the regression option, and then get the AMOS add-on. You are welcome to use our software. I'm just not going to support that within this course, but I'm happy to connect you with people who can support you, and you can work through it like that. So I want you to stop the video and reflect on these 4 things based on the introduction video. So I want you to literally pause, think about these, and then come back. Okay, so we're going to start with a model dissection. So in the guide, I want you to open this up and I want you to dissect all of the models that I gave you. We're going to specifically be talking about what kind of a model is it, how many observed variables, how many latent variables, which are independent, which are dependent, and what's predicting what. So we'll do a couple together. In this model, this is a full SEM, and I know that because I have latent variables, circles, with indicators, my items, and I have predictive pathways. So if everything was just curved between these, that would be a CFA. But because there are arrows going to C, it's actually predicting that, and that makes it a full structural equation model. When we talk about observed variables, these are going to be all of our indicators. So in this case, 3, 6, 9 items that are observed. We have 3 latent variables. Those are our 3 circles up here. Independent variables are 2, A and B, are both predicting C. So C is our dependent variable. It is being predicted by A and B. We don't know what A, B, and C are, but we could fill in any kind of variable name and start talking about conceptually why does it make sense that A and B predict C, but we'll come back to that. Here's another example. So this one, we have only curved lines. We don't have any predictive lines between our latent variables. So plan does not predict analysis. That's not a straight arrow. So this is a this is a CFA, not a full SEM. We can see that plan has 8 indicators, analysis has 2 indicators, feedback has 2, and revisions has 3. We do not count all of these error terms in our observed and latent variables. So you will see error terms on items. You will also see error terms. There's no circle right here, but those are indicating error terms for each latent variable as well. So in this case, we have 4 latent variables. There are no independent or dependent variables in a CFA. So everything is just like correlation. There's no IV or DV in a correlation. They're equal. So nothing is predicting anything. Here's the third one. This is a path analysis, and we know it's a path analysis because there are no circles with indicators. These are error terms for the 2 dependent variables. So here I have 4 observed variables. I have 0 latent variables. So they're squares, so I know that they're observed. There are 1, 2, 3 independent variables in this model. So I have attitude and social norms predicting intention, and intention also predicts behavior. So intention works as an independent variable and a dependent variable in this model at the same time. So I have 2 dependent variables in this case. And this is actually starting to get into mediation, where intention is kind of capturing some of the relationship between attitudes and social norms and the flow of effect between them into behavior. So I want you to stop and go to the guide and dissect all of the models that were given there. So go ahead and pause, and you can end with this one. It's super fun. All right, so we're going to get into model specification. This is the first step that we do in SEM models because it's literally what's the theory and drawing the models. So we can look back at all the models that you just dissected and think about what are these trying to do. So here we're trying to predict performance. Performance is the only true dependent variable. Everything else has at least one other thing predicting it. But performance is indirectly or directly being predicted by all of these. And so the model specification would be starting with, how did we even get all of this? Why is capacity predicting performance? Why is it being predicted by process and knowledge? Why does process predict knowledge, which predicts content, which predicts extent of implementation, which predicts performance? Where did all of this come from? How do we know that these are indicators of process? These are indicators of knowledge. These are indicators of capacity. That is what model specification is doing. So take a step back and really think about the theory behind things. Why would this concept connect to this concept? Okay, so now we're getting into model identification. I want you to put your finger on the screen on the cloud. I literally want you to pin down this cloud. You didn't hold it enough. Pin it down. Pin it down. That's what we're doing when we're setting the scale of estimation. We are arbitrarily pinning down a latent construct. These are in space. We can't physically measure them. So we're just going to pin one item, and we're going to use that as the established reference, and we're going to make everything else relate to that. So everything is relative in these measurements, and we have a kind of this starting point, and everything pins around that. And this is going to all be based on correlation and covariance matrices. So we know we're very familiar with the correlation matrix. This is just an unstandardized version of the variances. So these are standard deviations and variances instead of the standardized correlation. So when we have a latent factor with 3 items, so 1 latent factor, 1 circle, 3 indicators representing this 1 latent factor. We are actually estimating a lot of different things in this very simple model. We're estimating the loading for item 1 onto the latent factor, item 2, item 3. So what is the relationship between each one of these? How much are they kind of contributing to this whole? We're also measuring the error terms on each one of these, as well as the error term up here. This gets confusing because we only have so much information in our actual data. So this is the data that we have, the correlation matrix for 3 items, and we have 1, 2, 3, 4, 5, 6 different points of data. So if I lock this guy right here and just say that there's no error for the latent variable, this is called just identified, meaning I have 6 things that I am estimating, and I have 6 things that I know. So I have 6 knowns, and I have 6 unknowns that I'm estimating in my model. Over-identified is when there are a greater things to be estimated than we know. Under-identified is that we are estimating less we know less than what we're trying to estimate, and we can't do that. So we have to know more than we're estimating. So here's your first hint that if your model's not running, it's probably an estimation aspect, that you have more things that you're trying to understand than you actually have to estimate in the data. And a lot of this is based on degrees freedom. So it's, do we have degrees freedom left over? And if we don't, we end up with negative degrees freedom and we literally can't model it. So if we think back to degrees freedom from intro and intermediate stats, this is basically, it's the amount of things that we have assigned to a distribution. And so when we are estimating sample information instead of population information, we lose a degrees freedom. And that is the same in all of these. So every time we are using a sample mean instead of a population mean, we lose a degree of freedom. And basically what we're doing is we're trying to underestimate the statistical significance. We're not trying to overinflate things. So in correlation, for example, we sub in 2 sample means, so we take 2 degrees freedom. That's why the degrees freedom is always n-2. And the other 2 t-tests, it depends on if we have equal variance or not equal variance as to how the actual equation is modeled and what degrees freedom means. If we are pooling the sample or if we are considering the samples unequal and standalone. So if we have one indicator, one latent variable, and it is being predicted by one item. This doesn't make sense in a lot of ways, but we'll come back to that. So we have the variance, literally the variance of what x1 is. So that item, what is my standard deviation? What is my variance? That's all that we know. So we only have one thing, but we're trying to actually estimate 3 things. So the error term up here, the factor loading here, and the error term here. This doesn't work. So we can't do it. And also, conceptually, this doesn't make any sense because if I have one item trying to represent an entire construct, that doesn't make any sense. We need lots of items to represent something. It's basically you're trying to use one observed variable and pretend like it's latent, which it's not. So what we could do is lock the error to 0 and lock the variance in latent to 1, in which case we are now a 1-to-1 just identified, and that 0.64 variance literally goes right here. That's where it goes. That's not really that helpful in this case. So skipping through, when we get to 2 indicators, we're starting to get a lot more information. So just by having 2 items, we now have 3 different things that we know. Unfortunately, we're still trying to estimate 1, 2, 3, 4, 5 things here. We still don't have the identification that we need. We're still under-identified. So here, what we could do is lock some other things. And we could set our error terms here to 0 and lock this one. And now we're over-identified because I'm estimating 2 things and I have 3 pieces of data that I know. In which case my estimated parameters are 2 and my observed information up here is a 3. Once I get into 3 items, getting a lot more data, 1, 2, 3, 4, 5, 6 things that I know, and I have here 3, 6, still 7 things that I'm trying to estimate, which is an ideal, but still doesn't quite work. I can again lock my variable up here at a 1, and now I'm just identified at 6 and 6. But magically, as soon as we get to 4 items, we now have all of the information that we need to estimate everything that we're trying to estimate. So I now have trying to estimate 9 things, and I have 10 observed variables.